Okay, Chapter 8, Addition Reactions and Alkenes. So both of these subjects are covered extensively in Chapter 8. So the parts that I want to focus on in this video are going to be hydrohalogenation and hydration. So addition is simply the opposite of elimination. In Chapter 7, we discussed elimination reactions in detail, and if you remember, whenever we did an elimination reaction, whether it was an E2 or an E1 mechanism, we always formed a carbon-carbon double bond. And in Chapter 8, we're going to focus on adding to a carbon-carbon double bond and forming two new sigma bonds. So addition is simply the opposite of elimination. All right. So we can think about the pi bond in an alkene as either being, as being an electron pair donor, and we can think about it as functioning as a base, as is shown in the first reaction, or we can think about it as being shown, or think about it as a nucleophile, as is shown in the second reaction. And what's also important to notice here is that in both cases, whether it functions as a base or a nucleophile, that we form a carbocation, and the carbocation is trigonal planar, and that's going to become important when we look at the stereochemistry of these addition reactions. So alkenes in nature and industry, I mean, you could spend a lot of time looking at alkenes in nature, and you see here in limonene, there's a couple of double bonds in here. In cholesterol, if you've studied cell membranes at all, in biochemistry or biology, you would have heard of cholesterol and probably seen the structure, which also contains one carbon-carbon double bond. Also, alkenes found in industry, so from crude oil, we produce ethylene or isolate ethylene and propylene, and then there's a whole host of compounds that can be made from those two compounds. Anyhow, addition versus elimination. So these are equilibrating reactions, and which side the reaction is favored is going to depend on temperature. And it says here, the higher the temperature, the more important entropy is going to become. And the reason behind that is because if we raise the temperature, if we push the temperature up, the entropy term is going to get larger and larger, and then it can counteract, so to speak, the enthalpy term and render the delta G negative. So let's just look at this very carefully, but the point is this. In order for that addition reaction to be spontaneous, the delta G has to be a negative value, so it's got to be negative. Now we know that the enthalpy value is going to be negative because we're breaking a pi bond and we're forming two new sigma bonds, which are stronger than the pi bond. So what about the entropy term? So let's just kind of skip over this because we have already looked at that in detail in the previous chapter. But what about the entropy? So the entropy is going to be negative because we're going from two reactants to one product. So we're actually decreasing in randomness or disorder, so therefore our delta S value is going to be negative. Okay, so if we plug that into our equation, this equation here, delta G is equal to delta H minus T delta S. We know that our delta H is going to be negative, so that's what I've shown here. We know that our delta S is going to be negative. T is always going to be positive because it's reported in Kelvin. Therefore, we're going to have a negative subtract a negative. So that's like saying a negative and you're adding something to it. So in order for the delta G value to be a negative value, that means at lower temperature, this entropy term is going to be smaller, and therefore the delta G will be negative. If we jack the temperature, if we raise the temperature up, if we keep increasing that, then eventually this negative term can become very, very large, and then we'll be adding something, or we can add something bigger than this negative term, which would render the delta G positive. Therefore, that is why at low temperature it's going to favor addition reactions, and high temperature is going to favor elimination reactions. So hydrohalogenation is simply adding HX to an alkene, and the HX compounds that we looked at are HCl, HBr, and HI. So here we have a symmetrical alkene. Over here we have a symmetrical alkene. It says we're adding HBr to that at low temperature, so addition is going to be favored. And we add the proton and the bromine across that double bond. But that's a symmetrical alkene. And this is really important. If the alkene is not symmetrical, so if we have an asymmetrical alkene, then two regioisomers are going to be possible, depending on which carbon gets the proton and which carbon gets the halogen. So I have shown here the two possible regioisomers. And which one are we going to form? Well, we can answer that question, and there's a really good reason behind it too. And it was discovered by Markovnikov, and he called this Markovnikov addition. And the take-home message from this slide is that for the carbon-carbon double bond, whichever carbon carries the most or possesses the most hydrogen atoms, that is the carbon that is going to take the additional hydrogen atom. So for hydrogen, the rich get richer. Whichever carbon has the most hydrogens on it, it's going to take the hydrogen from our HBr in this case. So in this case, we have only one hydrogen attached to our carbon-carbon double bond, so it's going to take the new proton, and therefore our bromine is going to go to the other carbon. And like I said, there's a really good reason for that, and we look at the mechanism of that. But what he also found is that when peroxides are used, is that the opposite regioselectivity is observed. So we call that anti-Markovnikov addition. And in this case, the reaction mechanism, it says must be different. Well, it's definitely different, and that mechanism is not discussed in our class until Chapter 11 because it involves the formation of radicals. So we'll discuss that in detail in Chapter 11, but you do not need to know this mechanism for Chapter 8. However, you do need to understand the regioselectivity for Markovnikov and anti-Markovnikov addition, and you do have to know the mechanism for Markovnikov addition. So we can put here, no mechanism. You definitely need to know the mechanism for Markovnikov addition if you want to get through Chemistry 3101. So this is just a quick conceptual checkpoint that's taken straight out of our textbook. It just says draw the expected major product for each of the following reactions. So in each case, we only are going to form the Markovnikov addition product because we don't have any peroxides. And in each one of these cases, we end up with an achiral compound, so we don't have to worry about stereochemistry or anything like that. Anyhow, that's a question that we looked at in detail in class, but the take-home message is I've highlighted all the carbon atoms that have the proton on them. So the ones with the most protons, here we go in red. So again, the rich get richer, so the additional proton is going to go to each one of those carbons, and the bromine or the chlorine in the last case ends up on the other carbon atom. Okay, so here's the mechanism. So the mechanism is a two-step process. The first step is a proton transfer to form the carbocation, and if you notice in this case right here, that we form a tertiary carbocation. So tertiary carbocation. Okay. And then our bromide functions as a nucleophile, comes in and gives us our final product. And what I've drawn here is that if we were to do the addition of the hydrogen, the proton, and if we formed the secondary carbocation, that's a less stable carbocation than a tertiary carbocation, so that is not going to be a preferred mechanism. So that explains the Markovnikov addition mechanism. So the step with the highest activation energy, we call that the rate determining step. Sometimes you'll see that abbreviated, the RDS, the rate determining step, and that's going to always be the formation of the carbocation in all of these Markovnikov reactions. So this is just rehashing what I talked about a couple of slides ago. It says the two possible products. So this is the anti-Markovnikov pathway, and this is not going to be favored because then we have a secondary carbocation that is not going to be nearly as favored as a tertiary carbocation. So that explains why the rich get richer. So you can see the carbon atom that already possesses a hydrogen atom, or the most hydrogen atoms, which is only one in this case, is going to take the additional hydrogen. And this is the bottom line right here. Markovnikov product is formed because of carbocation stability. That's the driving force behind the formation of Markovnikov addition products. So if a chirality center is formed, then you're going to end up forming two products because you proceed through a carbocation intermediate. So since this is a carbocation, we know this is trigonal planar. And since it's planar is just a fancy way of saying flat, So since it's flat, that means when our nucleophile, the chloride in this case, when that attacks the carbocation, it can come from either face of the molecule. So in this case, we're going to get the two enantiomers, which are formed in equal amounts. And when we have a mixture of equal amounts of enantiomers, we call that a racemic mixture, if we have a 50-50 mixture of those. Okay, and this is just showing the carbocation intermediate with the empty p orbital and showing that there's a 50-50 chance that it could attack from either face of the molecule. All right, and with respect to rearrangements, so hydride or methide shifts, if they can happen, they will. So this mechanism here shows, again, the rich getting richer. So if we were to draw in all of our protons, you can see that this carbon has 2 protons. This carbon only has 1. Therefore, this carbon here is going to take the additional proton, which generates a secondary carbocation. But you can see that just through a hydride shift, we produce a tertiary carbocation, and that is how we end up with this product here. So on the next slide, the bottom line is this. The take-home message is that if a carbocation rearrangement can happen, it's going to happen. So in this case, you're actually going to see a mixture of products. And the major product will usually be the rearrangement product. So always be on the lookout for those rearrangements of carbocations, whether it be a hydride shift or a methide shift. Here's another example that comes directly from our book. So you have the solutions in the solutions manual. So it says, identify the reagents that you would use to achieve each of the following transformations. These would be perfectly reasonable questions for the Chapter 8 quiz. So the first one you can see is a Markovnikov addition, because this carbon has 2 protons attached to it. Therefore, it's going to take the additional proton, and this carbon here has no protons attached, so that's going to take the bromine. And in this case, we form an achiral molecule, so stereochemistry isn't important. And the next example is an anti-Markovnikov addition. So we could even write here, this one is a Markovnikov addition, so I'll just put Mark, and then this one is anti-Markovnikov addition. Okay, and what I want to point out here is that most students recognize, okay, I need HBr and I need my peroxides, but it's very important that you don't say, okay, step 1 is HBr and step 2 is peroxides. You have to know when steps are important and when they're not important. In this case, anti-Markovnikov addition, the peroxides must be added at the same time as the HBr. Otherwise, you would only get the Markovnikov product if you were to add them in sequential order. Okay. This next one here is, again, comes directly from our textbook, Predict the Products for each of the following reactions. This is just getting some practice recognizing new chirality centers. So you can see the first one, we end up with a racemic mixture. The second one, we get an achiral compound, because here we have a propyl group here, and we have a propyl group over here. So that compound we could just write achiral by it. And then the last one, usually in the book, instead of writing out or drawing the structures of both enantiomers, it will usually just draw one of them like this and then just say plus enantiomer as well. And on a quiz, that would be perfectly acceptable. Just write one structure and then put plus the enantiomer. Totally acceptable. Okay, and then draw the mechanism for this transformation. So again, the first step is just showing the rich getting richer, right? This is the carbon that has 2 protons attached to it, and this carbon only has 1. So therefore, the blue proton is going to go on this carbon atom here. And you can see in this case that we have a hydride shift. So we have a H, I'll just write hydride shift here. And note that I put that reaction arrow in one direction because that's irreversible. Our nucleophile attacks, and there you go. That's our final product. Okay, what else did we cover? Acid-catalyzed hydration. So adding water across a double bond. So what's water made out of? Well, H2O. So you can maybe write the Lewis structure like this if it helps. So we're going to be adding OH and we're going to be adding H across a double bond. And the same rationale is going to apply when it comes to our Markovnikov regio selectivity here. In our carbon-carbon double bond, this carbon has the most protons, only 1. The other one has no protons directly attached to it. Therefore, it's going to take the other proton and then our hydroxyl is going to go on the other carbon. The acid catalyst that's typically used is sulfuric acid, and those square brackets, that simply means that it's catalytic, that it's added in a catalytic amount. So that simply means less than a stoichiometric, 1-to-1 molar ratio. And then we talked about the leveling effect, and we explained why, when you add sulfuric acid to water, why the major component of what you have in your solution would be hydronium and not sulfuric acid. And that is why, even though you write H2SO4 as your reactant, when we write out the mechanism, what we would actually show for the first step, for the protonation step, and the subsequent steps as well, would be water and hydronium. So our first step would be this. So again, even though we don't write hydronium over here, when you see that sulfuric acid, a catalytic amount of sulfuric acid in water, we know that hydronium is the major constituent. Therefore, that is what we would draw in our reaction mechanism. And then it just says, this one here just discuss reaction rate reaction rate of the hydration of alkene. So it says the hydroxyl is added to the more substituted carbon of the alkene, Markovnikov addition. The more substituted the carbon atom is, the faster the rate. So that all this tells us, the more substituted, the faster the reaction. That just tells us that it must proceed through a carbocation. So that gives us evidence for the reaction mechanism. So this is kind of where we left off, was looking at the reaction mechanism, and I drew this first step a couple slides ago. So the first step is the formation of a carbocation. But when we have water functioning as a nucleophile, then we get an oxonium. So if we go to the next slide, you can see that we have our oxonium, and then the oxonium must be deprotonated by water. And then it's not shown, but I added it here, that we're going to reform our catalyst. So we're going to regenerate our hydronium, and then it's going to be ready to add to another carbon-carbon double bond. So, and you should be aware of this mechanism, and you should be able to draw the mechanism. This mechanism simply incorporates the Markovnikov addition of water across a carbon-carbon double bond, coupled with a hydride shift. So you can see there's a hydride shift here. So H shift. So you should always be on the lookout for those. And then we form this tertiary alcohol and regenerate our catalyst, of course, in the end. And that, I think, gets us pretty close to where we left off. Yeah, just a couple more things. So just with respect to the equilibrium between the addition and the elimination of water, so the addition of water to a double bond and the elimination of water from an alcohol to produce an alkene. So in this case, we exploit Le Chatelier's principle. Anyhow, so if we have dilute sulfuric acid, that means we're going to have a lot more water. That would push the equilibrium to this side. So if we want to form the alcohol, we're going to use dilute sulfuric acid. Oops. Let me fix that. And if we want to form the alkene, then we would use concentrated sulfuric acid, because then we would reduce the amount of water, which would push the equilibrium to the left. So again, sort of some nuances here, but you should be fully aware of when to use dilute sulfuric acid, that's to form an alcohol, and when to use concentrated sulfuric acid, and that would be to form an alkene. And you should understand why those products are formed as well. You should be able to rationalize Le Chatelier's principle. And again, with the hydration, the same thing as the hydrohalogenation. Since the intermediate is a carbocation, that would mean that when water attacks the carbocation, it can attack from either face of the molecule, and we're going to get a mixture of enantiomers, or a racemic mixture, if it's a 50-50 mixture of these two alcohols, for example. All right, and that takes us to section 8.6, which we haven't looked at yet, and that's basically covers what we need to know before getting into the rest of the chapter.